we're just going to add problems to this. So I've got 4 or 5 graph ones to look at, and some condense and expand problems out of 8.5. It really doesn't take all that much time to go through. When we're working with logarithms and we're graphing them, in order to be able to graph them without using a calculator, you have to be able to convert simple logarithms by hand, which means you're going to be working with 2 simple properties. Log base b of b equals what?
X.
1. And then log base b of 1 equals x.
B.
0. b to the 0 is 1, and b to the 1 is b. Okay. Using your rules. So what happens here is, in order to graph stuff, if I wanted to graph the log base 3 of x, I wanted to graph that, the values of x that I'm going to choose would be, I choose log base 3 of 3, and I do log base 3 of 1, because it gives me ordered pairs at 1 and at 0. I'm choosing values of x to generate the y's, changing these up. Okay. To that, we shift h and k, just like we had before. Horizontal, vertical. Let me clear my throat. I don't know. So, there's only 2 graphs to worry about. When you're graphing logarithms, we have a vertical asymptote. You're always going to have a vertical asymptote at x equal your h value. Your graphs will always be to the right of their asymptote, no matter what. So that means your domain is going to be always x that's greater than h. There is no range restriction, so your range will always be all real. I don't know if there's something up there. Oh, okay. Yes, ma'am.
You said the vertical asymptote equals what?
H, whatever your h is. So if there's no h, it's going to be at 0.
Okay.
These graphs only go one of 2 directions. If the b value is greater than 1, it's moving up and right. If it's between 0 and 1, it's moving down and right. That's the only way those 2 graphs look. When we plot them, you only have to plot 2 points and then just have to understand what direction they're moving. Okay. Graphing logarithms, out of all the different things that we graph, generally are the easiest ones to graph. Okay. Yes, sir.
You know what time we get out of this class?
When the bell rings.
1B. 2.0.
Right now it's time to do
He's tried to act so coy
I
about
got a
it.
bunch of answers all
Yes,
at
ma'am.
once.
So they can only ever be like the day?
140.
140.
Okay. So, all right, guys, come on. So let's look at an example. Yeah.
Never mind.
Go ahead.
No, I read it. I mean, I know how to read, so.
So if we do one,
Oh, no.
let's graph this.
Bless you.
And when we graph these, we're going to graph the parent function and the shift. Excuse me. All right, so when we start this one out, you want to label your parent function to begin with. I know my parent function is going to be y equals log base 1/4 of x. I use that to generate my 2 ordered pairs. Okay. I use that one to generate my ordered pairs. I'm going to have log base 1/4 of 1/4, and I'm going to have log base 1/4 of 1, which gives me ordered pairs at 1/4 and 1. Excuse me, 1 and 0. Because of the way the properties work. Okay. Those are kind of as difficult as this really gets. They're really, really easy to work with. Okay. So now it's a matter of plotting the 2 points that you have. 1/4 and 1. 1 and 0. On my parent function, where is my asymptote? 0, very good. There's no h, it's going to be at 0. Okay. So I have an asymptote, x equals 0. And I know the graph's going to look like this. Okay. Now the shift, a lot of times what people start to do when we have all these shifted problems, if we have our parent ordered pairs, write down your shift order pairs. We know it's going to be x, it's x minus 4. So is it going to be x plus 4 or x minus 4, which is my ordered pair? Good. I got to move everything to the right 4. So my ordered pair will be x plus 4, comma, y. Is it plus 3 or minus 3?
Plus 3.
Very good. So now what's 1/4 plus 4? 1 plus 3. 1 plus 4. 0 plus 3. Where's your new asymptote? X equals 4. So I have an asymptote at 4. Ordered pairs 4 1/4 and 4. 5 and 3. There you go. Go to the next problem.
There's no horizontal asymptotes in this, right?
There's no horizontal asymptote logarithms. Exponential functions have the horizontal asymptote, whereas the logarithms have the vertical asymptote. That's the difference between the two graphs. Okay. What's that? I'll do another. Let's do another. Can I go to a clean one?
Yeah.
Andy is so annoying.
Oh, Mr. Murphy, I found an extra calculator. Like, I found somebody's calculator.
Oh, do you have it?
No, I'll bring it.
Cool. Thank you. It's the thought that counts, I guess. Oh, you know, I almost bought you something for Christmas. Yeah, but I didn't.
No, I'm just letting you know I have somebody's calculator.
I feel like I thought you really liked it.
Probably your
but
calculator that the other's got.
I got excited because I thought you were for real. You bought me something for Christmas.
Crushing the hearts and souls since 1993. All right, so you start with the same thing, guys. Heads up, come on. We start with the same basic idea. I know my b value is greater than 1, so I know it's going to have to do that. All right. I know that my parent function is y equals log base 4 of x. I'm going to pick two values of x that work with these properties. Since my base is 4, what's the other x value I'm going to pick? 4. Easy. So I have the log base 4 of 4. That equals 1. So there's my ordered pair, 4 and 1. Then I do the log base 4 of 1, and that equals 0. So my other ordered pair is at 1 and 0. idea. Yes, Martine?
So for, if your base is greater than 1, then it goes.
Goes this way? Oh, I'm sorry, if it's greater than 1, it goes
it's
up and to the right?
And then if it's less, it goes down.
Correct.
Okay.
And that's the point, since there's only 2 ordered pairs you're really working with, putting this on there right off the bat to know what way it's gonna go does help out.
So,
There's only 2 ways. If the B is greater than 1, it's moving up and right. If it's between 0 and 1, it's down and back. So now each of these points, yes ma'am?
So the second one, lot 4, 1, 0,
Mhm.
I guess 1,
Yeah.
0. Will that always be true?
And that's what's nice. You will, with your parent function, one of your ordered pairs will always be 1, 0. Okay. Always be, sir.
So it gets you to coordinate, they just plug in the base into X
Yeah.
and plug in 1.
Okay. But we really substitute. We're not doing electrical work today.
So, when I graphed this on my calculator, it like cut it off,
Mm-hmm.
and is that like something that really happens, or is
What do you
it,
mean it cuts it off?
like, it, when it hits the asymptote, it like disappears?
Right. Because it's getting infinitely closer and closer towards the asymptote, and it's not going to show that up on scale on the
Okay.
on the window.
Alright, okay.
So there's your parent. To this, I have to shift them all. The shift is going to be, now my H value is what? -3. So it'll be X minus 3 and Y minus 5 for my new set of ordered pairs. 4 minus 3 is 1 and -4. And this will be at -2 and -5. So we plot those. 1, -4. -2, and -5. And then I have an asymptote at -3. So here's my final graph. Which means my domain is a set of x that are greater than -3. And my range is all. Okay. Yes, sir.
This isn't the other note, that if B was greater than 1, it would pop to the right. This one is down to the right.
You got it.
What?
It's still moving. Is it up and right? Down and left.
Yeah.
Oh my god. I don't know if he's being serious right
So if I'm moving up and to the right, and that thing is going down.
I thought you were like skipping it halfway to the right.
Oh, no. I see what you're saying. I plotted the parent graph and then I shifted. I always start with parent and then I
I
shift.
thought this was like talking about the shift, not like the graph.
No, it's the graph. It's the graph. So I thought you were trying to be,
No.
okay, yes, sir.
so what is this used for?
Logs. That make their heavier wood. I'll show you. Hey, Mr. Chess Player, come sign your name.
I got a newspaper.
Are you a grandmaster yet?
All right, that's me right here. Oh yeah,
Did you
check
beat
that
him?
out.
Wait,
Eating popcorn.
Wait,
All right.
is that Daniel?
Yeah, this is Daniel Alcaraz right here.
Always chill.
Sign his name.
I call him Daquan Alcatraz, actually.
Hey, dude, are you a grandmaster yet?
What the heck is that?
That is my signature.
Why do you It looks like something that my nephew did.
Don't. That's the idea. Nobody can copy that signature because I did it myself.
So let's combine this out with,
That was the idea. That's the idea behind the signature.
like I said, with the graphing, we kind of ran out. We probably could have stuck all that in on Friday because it wasn't that much there. But today with 8.5, the stuff that's in 8.5 is very easy to work with. And there's 3 basic properties of logarithms that we use. And the reason I have to show you guys these properties is so that we can solve the equations at the end of the day tomorrow and into Wednesday. Best guess as of right now, we might be able to get a test in Friday, but it depends on how far we get through expanding, condensing, and then how much more of the modeling we want to get done. If not Friday, it would probably wind up being Tuesday, just so you guys get an idea of that. So in 8.5, what you can do with logarithms is you can condense or expand. Now, when I'm expanding a logarithm, I'm not doing this.
Same.
That's me though.
I'm not expanding it.
I'm going to do that anyway.
I'm laughing my
What? You're out. You get to write that one down. That was great. That's perfect. We need a good marker.
Wait, I
Here.
completely missed what he said.
He said I'm laughing my ass off.
Awesome. You'll have to put it underneath cages there, or erase cages. It's fine.
Don't worry about it.
Now here's the thing: is he gonna spell asymptote right?
Don't tell him. Don't tell him. Why do you write the
Paxson, Danielson.
Oh my gosh, who's gonna be able to read that?
He's writing it.
So what happens here?
You got it.
I know reading this quote was pretty good.
Write your name.
No!
You're supposed to write his name.
Cooper, sign up the train. Cooper, sign up the train.
What is that?
Anyway, so what happens here?
Cooper, sign in the train.
So you can do stuff condensing or expanding. And what I'm going to do here is I'm starting with a logarithm that has multiplication thrown into it, which means I can rewrite it by expanding it into two separate logarithms. So if you have multiplication 2 times x, you can rewrite it as the following. Log base b of u times v, thrown in lattice here. This equals the log base b of u plus the log base b of v. The advantage of that allows you to simplify logarithms with coefficients. So if you have log base 2 of 4x, log base 2 of 4 is 2, because it's 2 squared. You can simplify things out. Right? There's a lot of little properties we're able to do. Yes, sir?
Do you have multiplication in the base?
No. So my example here, where I have log base 3 of 2 times x, that can be rewritten as the log base 3 of 2 plus the log base 3 of x. Like I said, this is going to allow us to solve multi-step logarithm equations by being able to break things apart and moving values. Log base 3 of 2 is some crummy looking number. I can move that to another side by subtraction, and then I can I can 3 by exponentially to get that x value by itself. There's a lot of little properties we'll be able to do to solve for crummy looking decimals. Is basically what this works out. The other property we talked about is division. So if I have log base 4 of x over y, well, that looks like this. I just subtract them. Take the top log base, subtract the log base in the bottom. That's how you split up a division problem.
Nice.
And again, the advantage of this is so that you can simplify either the numerator or the denominator depending upon the log base. Okay? Depending upon log base. Excuse me. So this example here would be log base 4 of x minus log base 4 y. Okay. Not too bad. And
Wait,
then the
don't change it.
last one,
Wait, don't change it.
not changing it. The last one, I'll just put underneath here, is when you have exponents. If I have log base 5 of x cubed. Whenever you have exponents, it's a new thing, sorry, I was just on the same page, that's all. There's only 3 of them. This is the same as saying log base b of x to the n, whatever it might be. Whenever you have an exponent with logarithms, you just rewrite it with the exponent up front. Whatever the exponent just goes in front of the log. Okay. So my example was log base 5 of x cubed. I would rewrite that as 3 log base 5 of x.
So then we actually have to solve this, or do we just have to transform?
We're just transforming it today.
That's it.
Yeah, because like I said, what we'll be able to do probably by the end of the day tomorrow is take some crazy looking equations and solve them using these properties.
But we don't have to do it.
Not yet.
So just,
Yes, do that.
so that's multiplication, you can divide that out, right? And after you do it?
Huh?
Like, if it was 3 log base 5 of x, you can divide 3 on both sides. And just-
Yeah,
okay.
yeah, exactly, and that's where we're getting to. Because if I was trying to solve for x and this had to equal 9, I would divide by 3, and then I would take the 5th power, it would be 5 cubed and all that stuff. So, yes, ma'am.
I don't understand what you're doing in the
Here, whenever you're dividing, it's log base numerator, subtract log base denominator. And then obviously we can have combinations of all of these.
So when you're taking a number, like say it's x plus y equals z, when you take it to the power, like 3 to the x, would it be 3 to the x plus y equals 3 to the z, or 3 to the x plus 3 to the y equals 3 to the z?
Write that down. My head hurts today. I don't know what you're talking about. No offense. Yes? Good.
What?
Write that down.
What is this?
Finish it. I can take something like this and simplify. I'm going to expand this. Okay? Yeah, I see. So if I'm looking at this, guys, if I'm looking at this, I have log base 8 of 64x squared. In this case here, you have multiplication as well as an exponent. You're going to have multiple properties put together, and in time you'll be able to shortcut some of this, but I'm going to take it and just rewrite it out. I know that I'm going to get log base 8 of 64 plus log base 8 of x squared. Which means I can simplify it even further. How can I rewrite 64 as base 8? 8 squared. So this is log base 8 of 8 squared. That property, base b of b, remember that one, what happens to the exponent of 2 then? It just drops. So this is going to be 2 plus, well, how do I rewrite that last one? Good. 2 log base 8 of x. Okay. What this is allowing us to be able to do is to break apart problems to solve for x when I set this equal to something. Okay. So if I had this set equal to some number, I would subtract 2, divide by 2, and I'd raise it to the 8th power, and I'd get my answer. No. Jeez Louise. Properties when you have natural logs, they hold the same thing, because natural log is log base e. It's just a different base. You just rewrite it with natural logs. So if I have the natural log of 3y to the 4th divided by x cubed, and I need to expand this one, instead of writing log base e each time, I'm just going to write natural log. It means the same thing. Notice you have multiplication, you have division, and you also have exponents. Here's where things can get messy. Whenever you have division, I'd like you guys to rewrite the numerator, throw it in parentheses before you rewrite the denominator. Because a lot of times in numerators, there's more than one thing you have to do. So you have to string all of that together because it's being subtracted at the end. All of that has to be divided. Does that make sense? All right. So you have natural log of 3y to the 4th. Splitting that apart further, you might be able to pick this up. It's going to be natural log 3 plus 4 natural log of y, using the exponent rule right away. Or do you want me to show that step first? We're okay with that? And then I subtract 3 natural log x. You just start to get more properties, you just start pulling them together. Like I said, you'll start shortcutting a couple things here and there, and it's not going to be horribly frightening. Okay. Condensing, I know we're running out of time. Condensing works the same way. Yeah, there's really not much to this. If I'm condensing something, I'm doing the same
At
basic.
this time, teachers, please excuse all classrooms in the west wing, first and second floor, down to
No, we're the east wing. Guys, give me a second here, because notice when you have this thing, there's addition between the 3 separate logarithms, which means what are you putting all this together to do? Multiplying. Everything's got to be multiplied. So you're going to have a log base 4. Well, it's 7 log base 4 of 2, which means it's 2 to what? 5 log base 4 of x. And that's how this is going to work. Okay. Yes, sir.
Is that 2 just a 2, or is it like written?
Yeah, it's just a 2. It's just a 2. Thinking of the numbers I had, I forgot to write them down from earlier. We can pull it up real quick. Yes, ma'am.
Would you simplify to 87?
What's that?
Would you simplify to 87?
No, you don't have to. You can. What's up? 2 to the 7th. You guys don't. You can just leave it as 2 to the 7th. It's not a big deal.
At this time, teachers,
You get you the
please
problems
excuse
here real
all
quick. Okay, guys.
classrooms in the
16.
east wing, first and second floor, down to
I have these for you. I have graphing 3 graph problems, and then the evens for the condense and expand. You should be able to fly through most of that stuff without too much of a hassle. Okay.
Mr. Murphy, I was watching Across the Universe this weekend,
Oh, yeah. I've never seen it.
the song Let It Be is in there,
Yeah.
and like I couldn't get over the Let It Be
Got around to
part.